So now that we've learned how to solve differential equations by separating and integrating, and we've also practiced some applications in different contexts, we're going to focus on one particular context today, and that is modeling exponential growth and decay. The first thing I'd like to talk about is why this differential equation represents exponential growth and decay. And that is because the rate of exponential growth and decay, which we use dy dt to represent, is directly proportional to the amount present. So mathematically, if we translate that sentence, we have our dy dt represents where the equal sign is in that expression. And if you remember from your algebra classes, a direct proportion is a relationship involving multiplication with a constant k to the amount present, which is represented by the variable y. So that's why on this side of the differential equation we have k multiplied with the amount present y. So our job is to recognize that any differential equation given to us in this format, even if the variables are changed, this format represents an exponential growth and decay. So what I'd like to do next is practice our separating and integrating to solve this differential equation and come up with the general solution for any exponential growth and decay differential equation. So it takes a couple steps to separate this, but if you multiply both sides by the differential dt and then divide both sides by y, you end up with your separated variables dy over y equals k times dt. And this is going to give us a great opportunity to practice those antiderivatives which present a natural log. And so we'll practice that general solution. So once I finished separating the variables, I went ahead into my integration step. I got the natural log of the absolute value of y equals kt, and then I remembered my unknown constant plus c. And this is that one differential equation that's the exception. We wouldn't want to plug in our initial condition yet. We'd want to start by exponentiating both sides of the equation to solve for y. So by exponentiating both sides of the equation, I was able to cancel the natural log function. You're left with the absolute value of y equals, and then on the right side, I did employ that property of exponents, which says the sum of exponents can become a product of your bases. So we have e to the kt times e to the c. And to safely remove the absolute value bars from y, I have to acknowledge on the right side that that could be a positive or a negative value. And I like to pair that with the e to the c constant. So this whole box becomes the unknown constant that I'm solving for, and then times e to the kt. And to solve for that unknown constant in my box, I'm going to need an initial condition, and I wanted to keep it very general, so I didn't want to just make up some numbers. So let's say, just by the definition of initial, we're going to use 0 for time, and for our y value, we're going to use this expression. You might hear it called a couple of different things. You could hear it called y sub 0, or often people will call that y naught. Either way you say it, let's go ahead and plug those t and y values into our general solution. So you might notice once you get those values substituted in that it actually doesn't matter that we don't know a value of k, because that e to the k times 0 is e to the 0, which is 1. So it ends up that our boxed unknown constant is actually equal to our initial value of y, or y naught. So to finish finding my general solution, I'll go back to that step right after I had removed the absolute value bars, that y equals. I'm going to replace my unknown constant in the box with what we just found to be y naught, and then it's times e to the kt. And so this final general solution is the solution you'll get anytime that you solve an exponential differential equation. So it doesn't matter what the initial amount is, what the relationship constant k is, they all solve to the same general solution. You might be wondering, why is it possible to use the same equation to represent both growth and decay? And it all depends on that constant k that we've been talking about that gives the relationship between the rate and the amount present. So if our k value or a constant is greater than 0 or positive, it represents a growth in the amount. And if that k constant is less than 0 or negative, it represents a decay in the amount. So to think about that idea in a more graphical or visual way, we know that an exponential graph is going to have very steep growth as long as that exponent of e is positive. On the other hand, if the exponent of e is negative, it shows a decline, or in this case, a decay. So let's look at this first example and talk about, there's basically two ways to approach this problem. One way is if you recognize this right away as an exponential growth and decay problem, and there is a plan B if you don't recognize it as exponential growth and decay. You can always solve this again doing all these steps, which I know you're more than capable of doing. But if you want to save time and energy, especially on the AP exam, you're going to want to train yourself to recognize that this differential equation is exponential growth and decay. So here are the two options. If you recognize this differential equation and you know its solution is what we just found, I like to call this the Yokit formula. I have no idea if other calculus teachers use that kind of memory trick, but it's always helped me. So we can recognize that and go ahead and just start with that. Or if you don't, and your nervousness on the exam or whatever the case may be, you can just go through all these steps to solve for that and end up with the same result. But let's say for today's purposes, since we just solved that out, don't really want to do that again, that we recognize right away that that was an exponential growth and decay equation. So once you recognize that that's going to be the solution to this differential equation, your only job left to do really is to plug in the values that they've given you in the problem. So I recognize that my y value at time 0 is 20. So for my y naught, I substituted 20. And then my k value is given to me as 0.5. So you put that in for k. You leave y and t as the variable expressions. And you've got your particular solution to the general solution of that differential equation, and you're done. And so this will most likely be a question on your multiple choice section. So if you recognize and don't have to solve that out, you'd be done with this question probably in less than 30 seconds. So when we get back together in class, we'll work out the rest of these examples, and it'll show you that this idea of exponential growth and decay can be applied to a lot of different areas and subjects that you might have talked about in your other classes. For example, in chemistry, you might have talked about the decay or growth of a substance. In biology, you might have talked about either population growth or decline, or the weight of an organism or animal. And then lastly, we'll talk about how this relates to money or finances, as you would talk about in an economics class. So I look forward to that.